Hey guys, we're going to do a video here on something called scientific notation. And this is kind of, one of these areas where, science and math kind of meet up. We use a lot of mathematics in science, and usually it's to simplify things and make things easier for ourselves. And that's what scientific notation is. It's a way of simplifying things. So I'm going to teach you just some of the basics, kind of introduce it today. And here's a definition. Scientific notation is a way to write very large numbers and very small numbers. In science, we often collect a lot of data and we often investigate things that have these huge numbers or these really, really tiny numbers. And sometimes it's nice to have an easier way to write those numbers. So that's what scientific notation is. Notation means it's a way of writing, and it's a way of writing very large and very small numbers. And I'm going to kind of introduce it in this unit because has a lot to do with exponents and powers, something we've been working on in class. So why don't I kind of show you some of the basics here by starting with this. In your notes, we're going to build a chart. We're going to talk about the notation, the meaning, and the number. And we're going to organize it a little bit. So if I go too fast, pause the video and write all this down. But here's the idea. If I have 1 times 10, we know what that means. Usually we'd write it like this in class, 1 times 10. We know 1 times 10 is just 10. But technically, when we do 1 times 10, 10 is to the, what we call the first power. And if I change this and I said, well, I'm going to do 1 times 10 squared. Okay, well, we know 10 squared is 100. So this is like 1 times 100, which is 100. 10 is kind of this interesting number where it's all, for us in math, we relate it all to the 0 at the end. If it's 10 squared, we know there's 2 zeros and it's 100. If it's 10 to the first, we know there's 1 0 and it's 10. And scientific notation connects these really large and really small numbers to the number 10 because it's an easy number for us to work with. So I'm going to make a chart of 10 powers here. If I had 1 times 10 to the third power, let's say, we know that'd be 1 times 1,000. There'd have to be third power, 3 zeros. Remember, that means 10 times 10 times 10. Well, that's 1,000, so this would be 1,000. If I had, let's kind of continue here, 1 times 10 to the fourth. That means I have 1 times 10 times 10 times 10 times 10. 4 10s being multiplied together. Well, that'd be 4 zeros, so that'd be 10,000. Count the zeros, 1, 2, 3, 4. So that's 10,000. And I'm going to continue here. 1 times 10 to the fifth. That'd be 1 times 100,000. There'd have to be 5 zeros in that number, meaning it's 100,000. And if I did 1 times 10 to the sixth, I would be doing 1 times 1, 10 to the sixth means I have to have 6 zeros. There we go. Which puts us up into the million range. So now what I'm going to do is write 1 million right there. And I'm going to stop for a minute because I could continue this chart forever. I could do 10 to the 7th, 10 to the 8th, 10 to the 9th, 10 to the 10th. And as I keep on going, all that's going to happen in this pattern is I'm going to continue adding a 0 to each number, adding a 0, adding the 0, adding the 0, making the numbers get very, very large. And the reason I'm showing you this is because this is how we do scientific notation. And what I mean is this. Let me show you. We'll do an example. Let's take a really large number. This is a huge number. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 zeros. If you were going to say this number out loud, this is 3, you call it sextillion, because you know how you have millions, millions, billions, trillions, quadrillions, quintillions. This is sextillions. So it's a huge number. And we wouldn't really want to have to write this number out all the time. We want to shrink it down. So here's what we do. We look at it and say, well, how many zeros are there? How many zeros? Well, I think we already counted. Didn't we say there was 18? You can count by threes here easier. 3, 6, 9, 12, 15, 18. We said 18 zeros. So really what we have here is we have 10 to the 18th power. If you multiplied 10 18 times over and over and over again, you'd have that many zeros. But since it's 3 sextillion, we're going to do 3 times 10 to the 18th power. And this is scientific notation. Scientific notation. And look how much shorter and simpler it is. Instead of writing out this huge long number, if I was doing some sort of science experiment or project or report or whatever, I would rather write it like this than this. So this is the easier, shorter way of writing this big number. So this number equals this number. So why don't we try a few different ones? That was a really big number. How about this? Here's a little bit of a smaller number. Again, it's the same strategy though. We're going to count how many zeros are in the problem. So I see 1, 2, 3, 4, 5, 6. So technically, this equals 10 to the 6th power. That's how many zeros are there. But since there's a 6, we do 6 times 10 to the 6th power. And that would be my answer. And really what that truly means, I want you to put a little thought cloud here, is that if you were to like jump on your calculator or do it by hand, if you were to take 6 and times it by 10, 6 times 1, 2, 3, 4, 5, 6, you're going to get, it's going to equal this big, large number. So we're just shortening numbers down. We're just using this little notation. A lot of people, when they have to write like a science report, are not going to want to write out these large numbers. They're going to want to write this and keep it simple and sweet and to the point. So pause the video on this next one and you try this one and see if you kind of have a handle on how to do this one. Okay, so hopefully you've unpaused the video, and if you've done what we've done in the last few examples, you probably counted the zeros and said, oh, it looks like 6 zeros, so 10 to the 6th power. And since it's 32, you probably did 32 times 10 to the 6th power. But here's kind of the thing. If it's 32 times 10 to the 6th power, I can do something extra to this. Technically, 32 has a decimal point right here. If I wanted to, I can move it over one more time and call it 3.2. And by doing that, it changes the problem to times 10 to the 7th power by moving that decimal one more time. And this is how we want to write our scientific notation. We want it down to a single digit tens place number. So we don't want to say 32 times 10 to the 6th. We actually want to say 3.2 times 10 to the 7th. And if you think about it, here's the decimal point on that original number. When we were moving it 1, 2, 3, 4, 5, 6, 7 places, it's really like this exponent explains the decimal movement. So exponent explains decimal movement. So if I say I have 10 to the 7th power, I move the decimal 7 times, and 7 times, it's very important to notice this, to left, making the numbers simpler and easier to write. 7 times left. So how would you do, something not as big and huge, but how would you do 75,000? What would your strategy be on that one? Yeah, you're going to see 3 zeros and you're going to think in your mind, oh, it's like 75 times 10 to the 3rd. But then you're going to take that decimal point and just go one more step and change it to 7.5 times 10 to the 4th. And that is your final answer. Or you can look at it and say, you know what, the decimals here, it's 1, 2, 3, 4 decimal places to the left. So I went 4 left. Okay, 10 to the 4th. There's another way of figuring it out. So that's kind of how we do our really big numbers, how we change really big numbers into scientific notation. Let's go the other direction now. How do we do really small numbers? So here's an example of a really small number, 0.000005. It's a pretty tiny number. So how are we going to do how many zeros do we have? 1, 2, 3, 4, 5. 5 zeros. How are we going to do this really small number a different way? Again, it's going to come down to decimal movement. This time I want to move the decimal to the right. I want to go 1, 2, 3, 4, 5 spots I see here, but I'm actually going to go a 6th spot over to here to move my decimal point, which turns this into just 5 point nothing. So it's just 5 really. But I moved it 1, 2, 3, 4, 5, 6 spots, so it's going to be times 10 to the 6th power. I moved it 6 times, but here's the catch. If I leave it as 5 times 10 to the 6th power, remember what that means? 5 times 10 times 10 times 10 times 10 times 10. 1, 2, 3, 4, 5, 6 times. Isn't that a really big number, not a really small number? So we need to do something to show that we moved it 6 times, but we moved it to the right this time. We went right with our decimal. We're working with a really small number, so the way we show that is we use a negative sign with our exponent. We say we went 10 to the negative 6th power, and that makes up our answer. So negative powers, negative exponents, tell us that we moved to the right versus left. So I'm just going to write a little note here. A negative exponent is what we're going to use. Negative exponent. Which changes this scenario down here. And if it's not times 10 to the 6th power, it's times 10 to the negative 6th power. It means each of these is a 1/10, 1/10, 1/10, 1/10, 1/10, 1/10. There's 6 of those, 6 little fractions. That's what makes this number so small. So let me show you another example here. Here's a small number. It's not extremely small, but it's small, 0.0035. We're going to move it. We're going to change it to 3.5 is what we're going to do. So we're going to go 1, 2, 3 decimal places. All right, so times 10 to the 3rd power. And then we're going to remind ourselves that we're working with a small number. We moved right with the decimal, so we're going to make a negative sign. 3.5 times 10 to the negative 3rd is our answer. Now there's one last thing for this video that's going to be important. How to reverse the process. So what I mean by that is you're reading a scientific paper, let's say, and you see that the scientist is working with a number, 2.7 times 10 to the 8th. You do in your mind have to remember what that number actually means. Is it a really big number or is it a really small number? What kind of number is it? Well, 10 to the 8th is a very big number. That means we have 2.7 times 10 8 times. It's like times 10, times 10, times 10, times 10, on and on and on 8 times. So really, if I wanted to undo the process, what I would do is I would take 2.7 and I would undo the decimal 8 times. I'd go back the other direction. 1, 2, 3, 4, 5, 6, 7, 8 times to figure out what this number is, adding a whole bunch of zeros in here. That's a big number. So 2.7 times 10 to the 8th kind of unfolds, and I see 1, 2, 3, 4, 5, 6, 7 zeros. So I'm going to write this number out. 1, 2, 3, 4, 5, 6, 7 zeros. And every 3 I'll put my comma. 1, 2, 3. And I have, look at that number, 270 million. It's a big number. So 270 million is 2.7 times 10 to the 8th power. I've undone my problem. Versus like this one down here, 3 times 10 to the negative 4th. That's not a really big number. That's a really small number. We're working with a negative power. So what that really means is that the decimal point that's here needs to undo itself and go back the other direction 4 times. 1, 2, 3, 4 times to here. So I'm going to insert some zeros where I need them. And I'm going to change this to 0.0003. It's a small number. So it's a fluid process. You need to be able to go back and forth with scientific notation because when you read it, you have to remember what it actually means. If it's a really big number versus a really small number. But a lot of times we're going the other way, changing the small number into scientific notation. So last one for the video. Pause the video and see if you can undo this one. Okay, so here's the answer. 2.4 times 10 to the 5th is a very big number. So we're going to move it 5 times this direction. 1, 2, 3, 4, 5. And we're going to insert our zeros that we need. And I see 4 zeros. So I see an answer of 2, 4, 1, 2, 3, 4. 240,000. That's our final answer. Okay, so I hope that helped. We'll continue to work on this in class, but it's kind of the basics. Thanks, guys.